So this topic today we are starting with the design of the circular tank, and this is a bit different topic than the previous one, and of course because the concrete tanks design and also the shape of the tank is circular, so there are some different kinds of forces. In addition, the application of this topic is understood because the tanks have been used extensively in the municipal and industrial facilities for many years, and special attention is needed to design these tanks not only for the strength requirements but also for the serviceability requirements, because managing maintenance of these kind of structure is not that simple. And already while construction, some additional measures should be taken to control the seepage, to avoid the corrosion of the reinforcement, and to have a reasonable service life without the undue maintenance. So a properly designed tank must be able to withstand the applied loads without cracks that would permit the leakage. So a tank that should not leak, a sound tank is needed that should not leak, and this is possible by providing the proper reinforcement, by providing the proper spacing and detailing of the joints, construction joint, quality concrete placed using the proper construction procedure. So standards needed to be followed for the circular tanks. The code that will be used for designing the tanks is ACI Committee 350, that is Environmental Engineering Concrete Structures, and essential in understanding the design of the tank. This code is giving us the lot of details for the designing of the environmental structures, which include the tanks, underground tank and overhead tanks, sewage treatment plants, and mainly the ACI 350 code and the ACI 350 committee reports. This present the recommendations for the structural design for the materials and constructions of the concrete tanks and reservoirs and other structures, normally which are used in the water, used for the water containment purpose, for industrial water, for wastewater treatment work, where the dense impermeable concrete with high resistance to chemical attack is required. So we can get a lot of guidance from this code ACI 350. Importance for the circular tank is the loading condition also. So load is not acting in the one direction, but it's possible that you need to design a same tank for different kinds of loading. Why? Because the critical condition for the tank is sometime the tank is full, and this is the first condition. When the tank is full, the load from the inside is acting. This is the first condition, that the tank is considered as the full tank. Second one is that the no load inside, so tank is empty and the load from the outside is present. First condition, the load from the inside of the tank is present. The second condition, the load from the outside of the tank is present. Now if you see the loading and the boundary conditions, you can say that the effect of the first case is opposite to the effect produced by the second case, and these two are giving us the opposite stresses in the walls and the base slab of the tank. And there is one more condition which is not all the time practically followed, but if the tank is covered and uncovered again and again, and let's say the load when the liquid is entered, the tank was uncovered, so you have to see sometime that the tank is covered also, because when you put down the fixed cover or hinge cover at the top, the additional load is also produced due to this cover, the additional movement and the axial load is also produced, which is not present otherwise. So therefore, you have to see that the different conditions are present, and the tank is not only designed for the single conditions but multiple conditions. The summary of this loading condition is like that: the tank should be may be subjected to the uplift forces from the hydrostatic pressure. This is the additional one force that when you are designing an in-ground tank, you have to see that whether there is an uplift soil pressure, because it is possible that due to the water table can come outside the tank and above the base of the water tank, and it can apply an upward thrust to the tanks. And what happens that the tank can be dislocated, and the pipes which are inserted in the tank can also be basically the joint of the pipe can be disturbed and the leakage may start. So we have to design the tank so that the empty tank should even be the weight of the empty tank should be larger than the total uplift force. So it is important to consider all the possible loading conditions on the structure. Full effect of the soil loads and the water pressure must be designed for without using them to minimize the effect of each other. And the effect of the water table must be considered for the design loading conditions. The critical load should be considered. We cannot consider the simultaneously load which are cancelling the effect of each other. For example, I have shown you the critical condition that I cannot say that the water is present also and the load from the outside is present also, but I will take it as a separate two condition. Condition number one is the water present, no soil is present. Condition number two is that soil is present, water is not present. So in this way, the opposite in the third point, that the critical load is considered, and this will give us the maximum effect. Then come the design of the methods for the circular tank design. So the factors are also different, and a bit modifications are also there in the tank design, and you can see that the load factor to be used for the liquid pressure uh, is 1.7 rather than 1.4. This is a one modification which was done in the ACI 350 code, that the load factor is modified. The second modification is that the sanitary coefficient is also introduced. This sanitary coefficient is basically multiplied with the required strength, so it is further enhanced. And the sanitary coefficient is 1.3 for the flexure. It is 1.5 for the direct tension and 1.3 for the shear. So these modifications are applied in the ACI 350 code. One another aspect of the design methods, that if you are not following the strength design, then of course you are not applying those factors. But why we should follow another working stress method? You know that working stress method means that the allowable stresses are within the lesser than the yield stresses or the ultimate strength, like the steel grade. If it is a 60 grade steel, you will use not 4500 kg per square centimeter, or you will not use 420 megapascal, but we will reduce that stress by half. So we will use half of Fy. So Fs is smaller, and similarly the concrete stress is also 0.45 of Fc prime. So it means that we are using the less stresses. When you are using the lesser value of the stresses, it means that this will be at the cost of heavy sections. So why we need the heavy section? Because historically, mm, we want durable structures and long life structures. That's why some of the engineers are following this method. for the design of the tanks. And even now it is followed. The working stress method is common. So that when I am designing the working stress method, although the design is a bit heavy, but we are well below the yield strength, so therefore the chances of the failure or the cracks are not there. Here normally what happens that when we are designing the thickness of the tank, we are using the working stress method because the larger thickness is obtained, and when we are designing the reinforcement of the tank, we are using the ultimate strength design method. So for computing the thickness, we can use the allowable stress and the working force, and for using the design, for carrying out the design, we are using the ultimate strength and ultimate forces. These are the combination for the design of the tank. When you are designing for the multiple combinations, then you can see the different combinations which are involved, where D is the dead load, F is the fluid load or any other liquid load, LR is the roof live load, D is the dead load, E is the earthquake load, and R is the rain load. So all the loads which may be present, and these loads are also explained, and accordingly the factor, you can see the first factor is 1.4 times the dead plus the liquid load. So when the liquid load is present and the dead load is present, this is 1.4 times, and when the live load is also present, then the factor is 1.2 D plus fluid plus temperature, and 1.6 times the live load. Then one more factor is also added, that the required strength should also be multiplied with the durability factor. So sometime we are multiplying our required strength with the durability factor also. The durability factor is SD, which is the ratio of the yield strength of the steel to the working stress of the steel, where working stress is also multiplied with the gamma. Gamma is the ratio of the factored load to the unfactored load, and phi is, whereas the yield strength, this is larger than 1, and yield strength is reduced by phi, the bending resistance factor. Phi is 0.9 for the bending, and that the same value are the used because the phi, for getting the phi value, you can see the curve between the phi and the strain, and it's same, like it is either a compression controlled section, then the phi is different, 0.7 or 0.65, and when it is a tension controlled section, it is of course larger than the 0.8, and it is 0.9 for the tension controlled section. This phi value is similar which have been used in the beam design. Next come the permissible stresses value. So for the normal environmental conditions, for direct and hoop stresses, when we are computing the hoop stresses or direct stresses in the tank there are different kinds of pressure. One is along the circumference, so the stress that is produced through the circumference. You have studied the topic of the cylinders, and you know that that stress is called as the hoop stresses. Due to the inward pressure on the circular tanks, the hoop stress is developed. So actually that stress developed the axial tension along the cross section of the wall. And second type is the vertical stresses or the shear stresses also, and the bending stresses. So the allowable stress value Fs, you can see that it is different for the different cases. It is 24 KSI or 165 megapascal for the shear. For the severe environmental conditions, It is 140 megapascal for the normal environmental conditions. It is 140 megapascal again for the hoop stresses and 120 megapascal for the severe environmental conditions. So these are the permissible values that we have to consider. And when you are designing the tank, you have to see these working stresses values for the shear and the axial force. And what is the allowable shear stress or the critical stress that is carried out by the reinforcement is equal to the stress carried by the shear reinforcement is defined as the excess shear strength required in addition to the design shear strength provided by the concrete. So the stress that is carried out by the steel is SD into VU minus 5 VC. The steel stress should be larger than this value. VC is the 5 VC is the shear that is carried out by the concrete. Similarly, the allowable flexure stresses, because the previously you have not seen the formula for the flexure stresses any value, then what value should be used for the flexure stresses? So for the flexure stresses, the allowable value is written in the form of the expression comprised of the beta, where beta is a fixed value for 1.2 for thickness of the tank larger than 40 centimeter, and it is 1.35 for the thickness of the tank less than 40 centimeter. S is the spacing of the reinforcement. dB is the dia of the bar. So we can see that generally the beta is normally taken as 20 ksi or 140 megapascal for the one-way members and 165 megapascal for the two-way members. It should be larger than that. So these are the limits of the flexural stresses. We can also see the flexural stresses from this curve, where S is the on the vertical axis and flexural stresses maximum limit is on the horizontal axis. You can see that the for spacing, maximum spacing allowed in the tank is 12 inches, and Fs can vary from 16 to 24 inches for this spacing. Maximum bar spacing is this one. Then after that, when the spacing is reduced, then you can see the variation is there. For the 10-inch spacing, the stresses is different, and minimum you can see that HS is larger than 16 inches. In this curve, the HS is less than 16 inches. Similarly, for the severe environmental exposure, the formula is a bit modified, and accordingly, the curve is also modified for the severe environmental condition. You can see the allowable flexural stresses limit from these curves or by using these expressions. Durability factor is basically also multiplied with the load also. So unfactored load is also required strength should be larger than the service strength by durability factor ratio, that is Fy over Fs, which is larger than 1. Now when you are computing the wall thickness of the tank, that is one of an important step, that how to compute the wall thickness. And as I have told you already, that the wall thickness will be computed by using the allowable stress design method. And this is not a straight wall but a circular wall, so you can take it as a segment of the wall. Consider a one segment of the wall which is thickness T is unknown. So you can take that segment which is 1 meter high and 1 meter length and thickness equal to T. Normally we use the important aspect is that when the water pressure is acting from the inside, it means that will develop a hoop stress that results in the development of the tensile stresses in the water tank. Tensile stresses are developed. So in the design of the concrete member, the tensile strength of the concrete is normally ignored, but you know that what is the here in the circular tank, we have to consider the limiting tensile strength, because the any cracking in the tank is unacceptable, and excessive tensile strength can develop a cracking in the concrete part. So we can provide the reinforcement also to control the tensile stress, that is the hoop reinforcement, circular reinforcement. That will be a circular reinforcement that in the tank. And secondly, we can also go for the more thickness, and if at the same time when the stress is applied, the concrete should also be capable to take that the tensile stress. If the concrete is not capable, then we can increase the thickness of the concrete. So how much is the maximum allowed tensile strength of the concrete? That is 7% to the 12%, or 10% of the concrete strength, the tensile strength will be used, equal to the 10% of the concrete strength. So let's say Fc prime is you can say is 20 megapascal, then you can take it as a FCT, the tensile strength equal to the 10% of that will be about 2 megapascal. And if you are using the 30 megapascal concrete or 27 megapascal concrete, the 10% will be 2.7 megapascal. So according to the ACI 350 reinforcement, cast in place concrete walls 3 meter high or taller, which are in contact with the liquid, shall have a minimum thickness of 30 centimeter. This is a general thumb rule that if your wall is high 3 meter, the thickness of the tank will be 30 centimeter. It is about L by 10. So if your wall is 2 meter high, you can have a thickness of about 20 centimeter. Normally your thickness of the tank cannot be lesser than the 200 millimeter. When the double mesh is provided on both sides, the reinforcement is needed, then it cannot be lesser than 8 inches or 200 millimeter, because the cover is also about 50 to 60 millimeter, so it is not possible to place the steel when your thickness is smaller. Now see the proof for the thickness formula. Let's say you consider a segment of a circular tank which is a t meter or t centimeter thick, 1 meter long and 1 meter high. Of course, the shrinkage is acting on the concrete, and shrinkage will try to shorten the concrete equal to the strain epsilon sh. Whereas the bars are also present, steel bar, which will try to uh, control that shrinkage strain, because these tensile strain will be in the opposite direction. So epsilon s is less than epsilon shrinkage, and the steel basically shortens the distance epsilon s and accordingly is subjected to the compressive stress Fs, while the concrete will elongate a distance epsilon sh minus epsilon s and will subject to the tensile stress Fct. So it means that the net strain that will be developed in the concrete will be the shrinkage minus the steel strain. You can say that the total shrinkage strain will be the sum of the concrete strain plus steel strain, and steel strain can be determined by the shrinkage strain minus concrete strain. So putting the values of the strain, because we are proving this formula for within the working stress design, so it means that you have to put the working stress value. Working stress steel is Fs over Es and epsilon sh, because this is equal to the some known value. Shrinkage strain in the concrete is already known, minus Fct over Ec. Epsilon c is Fct over Ec. Now further simplifying it and putting the ES on the right hand side, the equation becomes Fs equal to this one. And now we know that in the working stress method, the ratio of the modulus of elasticity of the steel to the modulus of elasticity of concrete is ES over EC. So here you can see the relationship as Fs is equal to epsilon Sh ES minus N FCT. FCT is the tensile stress of the concrete. Now we also know that as per the conditions of the, if the steel is also provided along the cross section of the member and the axial force is acting, so it means that the stress AS into Fs should be equal to the AC into FCT. So putting the value of Fs here, the from this equation, the value of can be put here, and it is the epsilon SHES, and it's further simplifying it. It comes out to the further simple formula of FCT, putting the values, and it can be written as this one can be further simplified into FCT equal to epsilon SHES. So this is the now formula for the allowable tensile stress. Initially, where epsilon SH is the shrinkage strain, ES is the modulus of elasticity of the steel, and AS is the area of the steel, and AC is the area of the concrete, and N is the modular ratio, AS is the area of the steel. Similarly, FCT is also tensile stress in the concrete is also equal to T over the total area. You remember the working stress method design. So total effective area is equal to the concrete area plus N into AS, the rotated area of the steel. So we can overall take it as a sum of these two stresses. So FCT due to the loading and due to the shrinkage strain. Taking the sum, FCT comes out to be this value. So this is the limiting tensile strain, which is written at the end. From this, you can find out the area of the concrete. If you are computing this stress value for the unit width of the concrete, you can put 1 meter into the thickness of the tank as area of the concrete. So thickness can be determined. N is known, AS is known, ES and epsilon SH is known, and force is also known. And if you want to compute directly the thickness, you can also compute the thickness just by putting the AC value. Let's say you are computing the thickness for 100 centimeter high concrete segment, then T is unknown and all other parameters are known. The FCT limiting tensile strain is also known. So you can bring the T on the left hand side and FCT on the right hand side. And by using the last expression written in the last line, this will give you the answer in the centimeter, because its 100 is put as the area of the concrete is replaced by 100 into T. And if you put the units in the other system of the units, like you have to be consistent in the unit. If you are putting in kg centimeter, then the answer will be tensile force will also be in kg. If you are putting in the pounds, then the tensile force will also be pound, and then the stresses should be put in the psi, and the answer will be in inches. But formula remains same, only the units should be consistent. So these two formulas which you can see here, or this last formula that you can see on this screen, can be used for verifying the thickness. Normally we assume the thickness initially and then we apply these expressions. If our tensile strain is well within limits, then we go with that thickness. And if our tensile strain exceeds, we can increase the thickness if the tensile strain is larger than the limiting strain. We can increase the thickness. By increasing the thickness, the stress reduces. The wall thickness formula is here written, and you can use the value of the shrinkage strain as 0.0002 to 0.0004. It's about 200 micron to 400 micron. For the plain concrete, it is 300 micron to the 800 micron shrinkage strain. Now, this is an example for computing the thickness of the tank. So let's say the FC is given, Fy prime and Fc prime is given, Es is also given. Then how to get the thickness? So first of all, you will, for these value of Fc and Fy, you can compute the thickness because FCT is 10%, I have told you. Then normally the tensile strength of the concrete is the 10% of the compressive strength. So multiplying with the 0.1 into 300, you can compute the thickness. Fs is the Fy over 3 for the axial stress, so it is 1400. Now you can put down all the values, but the units put here are in kilogram and centimeter. So you can see that after putting down all the values, the tensile thickness comes out to be the 0.0042 times T, because every values were put in kg, so it means that the tension should be put also in the kg. And how the modulus of elasticity of concrete can be computed? You know that it is dependent upon the Fc prime. So EC is 4700 under root Fc prime if you are computing in megapascal. It is 15,100 into Fc prime if you are computed in kilogram per square centimeter. So EC is computed and put down the value, you get this answer. If you want to get this answer in in another units, because here the answer of the thickness is 0.0042 T. So we get the put down the value of the tension in kg, we can get the thickness in the centimeters. If you want to put the values in tons, in the tension in the ton value, then we can multiply it with the thousands, and the answer will be T is equal to 0.42 times T, where this tensile force will be in the tons. So unit doesn't matter. Finally, you should understand that how to compute the thickness. The unit should be consistent. Then comes the reinforcement, because the reinforcement plays an important role for controlling the extent of the cracking. This should be sufficient for controlling the strength requirements and also the serviceability requirements for temperature and shrinkage effect. And proper detailing is needed by the designer for the reinforcement. And size of the reinforcement should be chosen such that the cracking can be better controlled by using a larger number of smaller dia bars. Because more spacing is not recommended. There is some limiting spacing in the tanks, not more than 12 inches, and also there is a formula for allowable spacing. Maximum allowed is 30 centimeter or 300 millimeter spacing for the reinforcement. Minimum cover is 50 millimeter, and the wall thickness should be sufficient to keep the concrete from cracking. If the concrete crack, the ring steel must be able to carry all the ring tension. And also the splices which are provided, because the dia of the tank is quite larger sometimes, the splices provided should not be in one line, but it should be staggered. So lap length should be computed. That is about 90 centimeter. And in such a way that this is a staggered lap length, that one lap is provided here, The next is provided next line, next here, then again the next is provided here. So lab provided is not in one line, but it is at staggered points. This is the limiting spacing expression. To control the crack, the maximum allowed spacing should be less than these formulas which are given. CC is the clear cover, Fs is the stress in the steel, which is 0.6 Fy is to be taken for this formula. Then when the work is stopped, then we have to provide the water stopper. Normally in the slab or structure which are constructed above the ground, it is not provided. But when it is a water tank, because sometimes the walls is quite, the tanks are not smaller structures. Sometimes it is very larger structure and we cannot make in one day. So maybe more than one pouring is needed. So wherever we stop the work and construction joint comes, you have to provide the water stopper. The water stopper can be of rubber material or copper material. Half of the water stopper is in the old concrete and the remaining water stopper is in the new concrete. Now next is the forces in the tank in the vertical direction, because we have discussed about the hoop forces which are in horizontal direction, because in the tank there are some hoop forces which are along the circumference, but there are also the forces which are acting on the walls of the tank. Now these forces depends upon the end conditions. There are different possible end conditions. Sometimes it is a free end or sliding end, sliding free joint or sliding joint. There is no monolithic connection here. So this will not take any moment because this will show the deformation. The pressure will vary from zero. You know that the liquid pressure is zero at the top and maximum at the bottom. But due to this effect of the force, the movement is not carried out at the fixed joint. This results in the larger ring tension will be present in this case, because the larger horizontal force is dominant and the vertical force is very movement is not resisted by the tank. Second case is the when the wall is fixed with the base. So when the wall is fixed with the base, then you see that the reinforcement from the wall is extended into the base and it is a quite monolithic connection. So this result in the zero slope at the fixed end, then the positive movement, then again the negative movement if the top end is also free. Fixed. Top end is also fixed. The load distribution will be like this in this tank, that larger load is there in the, it's like that, and this is the triangular load applied by the water. So this tank will take a reasonable movement at the base, and it will develop the tension on the water side initially. You see it's bending like this. First the tension is on the water side, then the tension is on the outside, then again the tension is on the water side. So initially it's the tension is developed on the water side, then the tension is developed on the outer side. If it is a rectangular tank, then this kind of condition, the elastic curve is different. But when it is a circular tank, its elastic curve is different. We need to analyze the tank properly, because this structure is a folded or the plate type of structures which are considered as a shell structure or circular structures. So behavior of the circular structure is different than the rectangular structures. Then comes, so overall, then come the hinge joint, the third one. The hinge joint is the joint which is not taking the movement. Movement is zero, but slope is not zero. So bending is like that. But this will also develop some kind of the more positive movement or tension on the outside of the tank. because again the fixed end is not taking the moment. There is no bending moment at this location. There is no bending moment. The reason is the hinges are provided. How we can make the hinge joint practically? by making all the reinforcement crossing at the corner. जो corner है आपका उस पे अगर हम cross कर दें ऐसे, and this the joint, the cross is exactly at the interface of the wall and base slab. When the cross is exactly at the interface, this will develop a zero bending moment. So these are the conditions for the tanks, and we have to analyze that these tanks, and we have to follow for the different conditions. There are different tables that we need to follow. If the bottom is fixed, then the coefficients are different. When the bottom is hinged, then the coefficients are different. So for every conditions, hinge base, the coefficients are different. Tensile force, hoop tension is different, and bending moment is present. When there is a fixed base, then the bending moment is also present. So we have to follow the coefficients for designing the tanks. These coefficients are given by the PCA, and although I have found these coefficients very helpful for finding out the forces in the tank, because there are overall 20 tables are given for the different cases. Triangular load, also the UDL, and also the trapezoidal load, the shear value for the circular slab coefficients. So you can say based on this discussion that the sliding edge will take the zero moment, and in case of the sliding edge, that was the first case, this first case, the sliding edge, this case. Second case was a fixed end, third was the hinge end at bottom. So sliding, there is a no movement, so total pressure is resisted by the ring action. Ring action is dominant in the sliding bottom edge. Second case was the hinge. Third case, again the ring tension is dominant, but the maximum bending moment take place at the middle part of the wall. In case of the sliding edge, there is a no bending moment, but ring tension is dominant. Then is the fixed bottom edge. When the fixed base is there, which is a common case, the water pressure will be resisted by the ring action in the horizontal direction and cantilever action in the vertical direction. So maximum ring and maximum positive moment will be smaller than for the hinge bottom edge, while relatively larger negative moment will be introduced. What happens that when I consider it as a hinge bottom end, larger ring tension is produced and lesser movement is there. But when I consider it as a fixed bottom, larger negative movement is produced in the vertical direction and lesser ring tension will be seen. You can see from the coefficients, when you will see that the coefficients values are quite larger when there is a hinge for the hoop tension, when there is a hinge base, and the coefficients values are smaller for the hoop tension when there is a fixed base. So practically, what should we do? We should take the critical conditions. For designing the tank for the hoop tension, I will take it as a hinge base, and for designing the tank for the negative movement at the bottom, I should take it as a fixed base. So taking the critical scenario, you can get the maximum effect. This is written also here that it is better that base should be fixed. It would be rare that the base is fixed, and it's better that base is hinged for computing the hoop tension. For conservative design, for mall monolithically with the floor, it is recommended to design the section at foot of the wall for the negative movement and maximum positive movement also, but the ring tension from the hinge base assumption should be considered. So in this way you can compute the forces, and we will now discuss the coefficients, and also the how to see the coefficients for the circular tank design. We will also do the problem. These coefficients are normally given for the pound fit system, and PCA coefficients are not available in SI system. So we will follow these coefficients and also solve one problem for the circular tank using these coefficients in the next part of the lecture. So thank you, and then you can have a break now, and if you have any question you can ask.
Excuse me, sir.